Okay, so today I'm going to be talking about partial derivatives and then tangent planes, and I think I'll talk about the differentials as well. Okay. And then after that, if I have time, then maybe I'll take some questions if you guys have any in general, or I might talk a little bit more about other stuff. Okay. So let's start with partial derivatives. Actually, maybe before that, if I could just confirm, can you guys maybe tell me like what are some of like last or most recent topics that you've discussed in class? You guys have talked about partial derivatives at least, I'm pretty sure, right?
Also implicit differentiation.
Okay, cool. All right, I'm good. I just want to confirm. So partial derivatives, so you guys should be familiar with how to compute them, right? So if I just give you guys an example, let's do fxy equals, let's see here, let's do x sine x squared sine of x y cubed. And let's throw in a little extra, it'll be minus 2x plus y squared. Okay? Alright, so let's compute the partial derivative of f with respect to x. So as you guys know, that you kind of have these two different notations for it, right? And in order to compute the partial with respect to x, so the way it works is you treat all the y's as if they were constants and just differentiate with respect to x, all right? So can you guys maybe help me out on getting the partial derivative? So if I'm doing it with respect to x, how would you get the derivative of this first part with respect to x?
First you could do like 2x times sine xy cubed.
Yeah, and then?
And then you'd have, would it be plus x squared?
Yeah.
And then that times cosine xy cubed, and then that times y cubed.
Oh yeah, very good. So in particular, we had to use the product rule. So we had a product of two functions of x, right? And then there was a chain rule on this one, which is why you're multiplying by the extra y cubed. Okay, very good. After that, what would happen next?
Then you would have minus 2. And the constant at the end is 0.
Alright, good, okay. So you guys all sort of comfortable with computing partial derivatives? Alright. So let's just do the partial with respect to y as well. Okay, so with respect to y, what would the derivative be?
Would this be x squared cosine xy cubed times, or
x,
wait.
Right? Would the x
Alright,
times x
sorry, what was that?
times x because of chain rule?
Not quite. A little bit more than that. So you have the right idea of using the chain rule.
Would it be times 3y squared?
Oh wait, 3y squared.
That's right, yeah, exactly.
Coefficient.
Yes, okay. So maybe we'll write it as 3xy squared, okay? Alright, good. Alright, and then after that, what would we have?
Plus 2y.
Yeah, plus 2y. Alright, any questions about that? No? Okay. Alright, good. So you guys do want to be a little bit familiar with like product rule, quotient rule, and chain rule, okay? Alright. I'm going to do another example, but I'll make the function a little bit easier this time. Okay. Alright, so you guys tell me again, partial with respect to x would be?
Um,
Uh,
4x
4xy.
Okay, yeah.
minus y squared.
Okay.
Plus 2x.
Alright, and then with respect to y, we would get
2x squared
mm-hmm.
minus 2xy
Okay.
minus 5.
Okay, I believe that is correct, alright? Is everyone good with that? Alright. So I wanted to do this second example because I wanted to just also introduce the second order partial derivatives, alright? Yeah, so we understand this being as like partial f with respect to x, partial f with respect to y. So the idea is we can also compute the partial derivatives of these two functions now, right? Okay, so fxx. So that will be the partial derivative of fx with respect to x, okay? And the alternative notation for that, in case you guys see it, looks like this. Okay.
So it'd be like 4y
Yeah, okay. Yeah.
plus 2.
Yes, all right, very good. And then if I want the partial of fx, but with respect to y, okay. Here's the sort of alternative notation for it.
Would it be just negative 2x? Oh,
Let's see
xy.
here.
Okay.
Let me see, with respect to y. Alright, yeah, so partial derivative of fx and with respect to y, what would that give us?
So it would be
Mm-hmm.
4x
Okay, good.
minus 2y.
Yeah, alright, good. And then let's just get the remaining two. So let's take fy, and then let's find the partial derivative of fy with respect to x, and then the partial derivative of fy with respect to y. Okay?
That would be the same for x minus 2y.
Ah, okay, yeah. So if you check it, you get the same thing for x minus 2y.
And then f of yy
Mm-hmm.
would be 4x minus 2x.
Fyy.
Oh wait,
Check.
sorry. It
Uh-huh.
would be just negative 2x.
Yeah, alright, good. Yeah, okay. So these guys are usually called the first order partial derivatives. Okay. So then all of these guys here, these are all the okay, sorry, I thought I was about to sneeze. So these are all the second order partial derivatives. Okay. And as you guys seem to already know, fxy happen to be equal to fyx, right? And so that's not a coincidence. That will always be the case for the functions that we deal with in this class, all right? So it's technically not always true, but for like all the nice functions that we'll be working with in this class, it'll always be true. So it's always the case in this class. Okay. Okay. So let's talk a little bit about what partial derivatives like actually are. Okay. So we know how to compute them, but let's try to understand what they are. Okay. So I'm going to draw a picture right now. Here's my x, y, z-axis. And let's suppose I have some surface. Okay. And let's say the surface is the graph of some function of two variables, f of x, y. Okay. Now, let's say I have this point x naught, y naught in the xy plane. All right. And then this point directly above it on the surface, that would be the point like x naught, y naught, and then the z-coordinate would just be like f of x naught, y naught, right? So the function just gives us the z-coordinate. So if we imagine like walking along this surface parallel to the x-axis, let's maybe switch colors, that might look nice. Yeah, so imagine I'm trying to walk on the surface parallel to the x-axis. Maybe I'll be walking around some curve like that. Okay. So the partial derivative of f with respect to x at the point x naught, y naught, it would represent the slope of that curve. Okay. As we are moving in the like positive x direction. Okay. So that's what the partial derivative of f with respect to x represents. It's basically like the slope. See, I'll write it like this. So it's like I'll write it as the slope of the surface as you move in the positive x direction. Positive x direction. And I guess I would say maybe like above or at the point. X naught, y naught, and then again, as I said earlier, the z-coordinate would be your function evaluated at x naught, y naught. Okay? All right, so does that make sense to you guys, what I'm trying to say? Okay. So the partial derivative with respect to y would be similar. So imagine like you're standing on the surface and you're trying to walk in the positive y direction. Okay. Then the slope of this curve that I've drawn in blue, that would be what the partial derivative of f with respect to y represents, okay, at this point. All right. So partial with respect to y at the point x naught, y naught. So it's similar, it would be like the slope as you move in the positive y direction. At the point x naught, y naught, and f of x naught, y naught. Okay? All right, any questions about that? Okay. All right. Now, one of the things that we can use these partial derivatives for is for finding the tangent plane to a surface at a certain point, okay? So I'm going to talk about tangent planes next. And tangent planes, and I guess at the same time I'm also going to talk about the linearization. Linearizations. And I want you real quickly just recall the notion of the tangent lines to curves from like Cal 1. So just real quickly. So here in the xy plane, let's imagine I have some curve, which is the graph of some function f of x, all right? So at this value x naught, and then at this point on the curve, whose y-coordinate would be f of x naught, okay? So the tangent line to this curve will look something like this in my picture, okay? And remember that we can get the slope of the tangent line from the derivative of our function, right? So if we want to write out the equation of the tangent line, so if we use like the point slope form for the equation of a line, okay? We know that this line passes through the point x naught, f of x naught, okay? And then we know the slope of the tangent line is given by the derivative of f at x naught. Okay. So here we could write the equation of the tangent line in this form. So the equation of the tangent plane looks very similar to that. So now let's imagine that we have, again, some kind of a surface. Okay. And then at a certain point on the surface, okay? And again, we're assuming that the surface is like the graph of some function f of xy, all right? So you can sort of imagine, I'm not the best drawer, but you can sort of imagine having a plane that is tangent to the surface at this point, all right? And to get the equation of the tangent plane, all right, so it's very similar to this, but on the left-hand side, instead of having y minus f of x naught, we're going to have a z minus f of x naught y naught. And then on the right-hand side, instead of having like f prime, we're going to have the partial with respect to x. Okay? I'm going to zoom out a little bit. Okay. So we'll have the partial f with respect to x at the point x naught y naught times x minus x naught. Okay? And then we're going to have the same thing but with y. So partial of f with respect to y at this point, and times y minus y naught. Okay. So then this would be the equation of the tangent plane. All right. So hopefully you guys can sort of see the similarity with the equation of the tangent line, okay? Now, oftentimes, this f of x naught, y naught, they'll oftentimes write it as z naught, okay? So sometimes you'll see the equation written as z minus z naught equals everything else, all right? Okay. So before I do an example, I also want to touch on the linearization, okay? So let's look at this picture again of the tangent line to the curve. So can you guys tell me what is so special about the tangent line?
It's touching the original function.
It is, yeah. But I guess, I can draw tons of lines, passing through that point, right? So what's special about the tangent line in particular? Uh-huh. Yeah, so I guess the idea is like the slope of, that's one thing. So the slope of the tangent line is kind of representative of like what the slope of your curve is at this point. Okay. There's actually something else though, which they maybe don't emphasize too much in calculus, but if you look at the picture, you notice how like near this point, how the tangent line and the curve are basically like indistinguishable from each other. So one of the like primary like applications of the tangent line is to use it as like an approximation to your function near that point where it's touching. Okay. So what I'm going to do is I'm going to take the equation of the tangent line that we have over here. I'm going to add the f of x naught to the other side. Okay. And instead of writing like y equals this, I'm going to write this as like a function of x. And I'm just going to use like L for my function, so I'm going to call it L of x. So this function here is what we call the linearization. Okay. So linearization, I guess, of this function f. I guess we would say at the point x naught. Okay. And one of the main uses of the linearization is that the linearization should be approximately equal to the function itself if we are close to the point of tangency, if you will, okay? So if x is close to x naught, it should be that the linearization should be close to your function, okay? And we can basically do the same thing on this side. So if I just move the z naught term to the right-hand side, so we'll have like a z naught, and I guess I'll write it as z naught because that's easier. So z naught plus fx times x minus x naught, and plus fy times y minus y naught. So again, if I, instead of writing this as z equals, I write it as like a function of xy equals. Then this function that we get would be the linearization. Okay. Of our function f. At the point x naught y naught. Okay. And again, the key application of the linearization is that if we have a point xy, which is close to the point x naught y naught, then our linearization at xy should be about the same as the function f itself at the point xy. Okay? So tangent lines, tangent planes, linearizations, all of them are related to this idea of like approximating your function with something linear. Okay? So let's do a couple of examples. Well, at least one example. Okay. So let's make up a function. I'm going to have f of xy equal to. All right, so I don't want it too complicated, so let's do x squared y cubed minus 3x, and let's just do 3x squared, and let's do plus 4y. Okay. Okay. And let's say for this function, we want to find the tangent plane. At the point, let's do at the point 1, -1. Okay. Then let's say if we want to also get the linearization, okay, at this same point. And then let's say if we want to, after that, approximate my function f at, let's do the point 1 point, let's do the point 0.9, let's do -1.1. So we'll approximate that using the linearization. Okay? All right. So were there any questions? Okay, all right. So let's first get the equation of the tangent plane. All right. So let's recall that this was the equation of the tangent plane. So let me try to copy this over. Okay, all right. So in order to get the equation of the tangent plane, we need to compute a couple of things. We'll need the partial derivatives, right? And we also need to compute z naught as well. So let's get, let's plug in the point into our function first to get z naught. So plug in 1 for x and -1 for y. So we'll get -1 minus 3 and So minus 4, right? So we should get negative 8. Okay. All right, sometimes I'm really bad at algebra, so if you see me make a mistake, you have to let me know, okay? All right. Next, we need the partial derivatives as well. So next, let's get fx. All right, who can tell me the partial derivative with respect to x?
2x by 2 by cube.
Okay.
minus 6x.
All right, good. Let's also get the partial with respect to y.
X squared 3y squared.
Okay, x squared and 3y squared, good.
Plus
Plus
4.
4.
Yes, okay. So we have the partial derivatives, that's good. Now we need to plug our points into the partial derivatives, right? So let's do f at 1, negative 1, sorry, fx.
Would it be negative 8?
Yep, actually negative 8 again, that's a coincidence. And let's also do fy at 1, negative 1. Okay.
So negative 3. 1.
So I think it'll be y squared make it positive. So I think it'll be 3 plus 4.
Oh, okay.
Okay. All right, no problem. Okay. Okay, so then now that we have these three numbers, we would just plug them into our equation here, here, and here. And then for x naught, y naught, we will plug in the 1 and the negative 1. Okay. So equation of tangent plane. We can write it as z minus a negative 8. So I'm going to write z plus 8, okay? Equals fx at the point, so it was negative 8, times x minus x naught was 1. And then we have plus fy, which is positive 7. And times y minus y naught.
So e plus 1.
Yeah, minus negative 1, so plus 1. And then that would be the equation of our tangent plane. All right, any questions about that? Okay, so the linearization is really simple after you have the tangent plane. So remember, to get the linearization, all we do is move this number to the other side. So, and then I'll call the linearization L of xy. So it'll just be negative 8 minus 8 times x minus 1, and plus 7 times y plus 1. Okay?
Oh,
Yeah, all right, good. And then finally, let's see here, part C, I will do it down here. So this point that we're trying to evaluate our function at, so notice how at this point is really close to the point 1, negative 1. So therefore, I could approximate my function using the linearization that we just found. Okay. All right. So instead of plugging into the function, we're going to plug it into the linearization to get an approximation. So let's see what we'll get when we plug everything in. So plug in 0.9 for x. So 0.9 minus 1 will be negative 0.1. Okay? And then we also have plus 7 times, okay, so for y, if we plug in negative 1.1 for y, it'll be, I guess, negative 0.1 again, okay? And if we just multiply and add all that up, this would be,
Negative 7.9.
yeah, negative 7.9, all right? So without using a calculator or anything, we can estimate our function at this point to be approximately negative 7.9. Okay? All right, any questions about that? Okay. Now I want to talk a little bit about the differential, okay, as well, all right? So let's see here. Let's go back to the equation of the tangent plane, which I have here. All right, so on the right-hand side, everything that we have here on the right-hand side is what we call the differential, which we denote by dz. And I guess I'll call it the differential differential of z. Okay. I personally don't really like the terminology here, but that's what they use. Okay. And oftentimes, people often write x minus x naught as dx because it's like a change in x. And people often write y minus y naught as dy as like a change in y. So sometimes you'll see the formula for the differential written as like fx dx plus fy dy. Okay. But keep in mind that the complete formula is this one up here, I would say. Okay. So looking at the linearization. So remember how the linearization was just moving this term to the other side? So you could write the linearization as L of xy equals f of x naught y naught plus dz. Okay. All right, and then remember the idea of the linearization is that it's approximately equal to your function at xy if xy is close to x naught y naught. Okay, so here I'm just going to move this term back over to the left-hand side. So if I do that, then here you kind of see the interpretation or sort of a significance of the differential, and that the differential gives you an approximation to this difference here. Okay. So you can sort of see that the differential is an approximation. A change in your function, like near a change in function at 2 nearby points, I would say. Okay. And since your function is representing like the z-coordinate of a point, you can say that it approximates the change in z at 2 nearby points. Okay. So that's kind of the significance, if you will, of the differential. And I sort of feel like it's not super important myself, but I know it's something that you guys can talk about, so I just want to talk about it as well. Okay. So let's just do like a quick example just involving the differential. Let's just create a relatively simple function. Let's do actually I have an idea. Okay, let's do this. So I'm going to make up another example right now. So let's say we want to approximate. I'm going to do approximate the square root. Let's do 2.9 squared plus let's do 4.2 squared. So let's try to approximate this using linearization slash differentials. Okay. All right. Okay, so this problem is a little bit different. So it asks us to approximate something using like the linearization, but they don't give us a function, right? So they don't give us a function, and they don't give us like a point x naught y naught or anything like that. So that means what we have to do is we have to come up with a function which would be appropriate for this problem. All right. So just looking at what we're trying to approximate, what do you think would be a good function to use? Any idea? Okay. Well, I don't know, like what we're trying to approximate looks, yeah, it looks like it's coming from a function like this. F of xy is the square root of x plus y squared. So in other words, they're asking us to approximate f at the point 2.9 and 4.2. Okay.
If it were the test, would that equation be given?
I do not know. So I think it's certainly possible that you might have a question like this, but you should be able to then like come up with the functions. I would say somewhat readily from what they give you though. Okay. All right. Now, in order to approximate our function, so let's say I might try to use the linearization over here, right? Because this says that our function is approximately the linearization. And the linearization is f of x naught y naught plus the differential dz. But we need to know like what point x naught y naught that we want to use in the problem as well, right? So do you guys have any maybe feeling perhaps as to what the point x naught y naught should be? what should we use?
4.
Yeah. So your point x naught, y naught should be nice numbers, close to the xy that you're trying to approximate at. So the nicest numbers we could choose close to xy would be 3 and 4. Okay. All right, good. So now what we want to do is compute the linearization. Okay, so to get the linearization first, let's plug the points into our function. All right. So if we plug in 3, 4 into the function f, what would that give us? Zero to 3 squared plus 4 squared? Yeah, gives us 5, okay. Now we also would need to compute the differential, all right? So the formula for the differential is up here.
So you have to find like the partial derivative.
Yeah, so we need the partial derivatives with respect to x and with respect to y. Okay? All right, who could tell me the partial with respect to x?
Would be
Uh-huh.
1/2
Yeah, that's right, uh-huh.
x squared plus y squared
Mm-hmm.
raised to the -2. Wait, no.
Ah.
Raised to the -1/2.
Negative 1/2, yeah, so half minus 1.
And then times 2x.
And then fy will basically be the same thing.
Oh, with the y.
That's right, yeah, okay. So let's go ahead and cancel the half and the 2. And I'll just write it as x times that, okay? And then fy is just y times the same thing. Okay. So, and I guess I'll write it as over square root x squared plus y squared. Okay. And then we want to plug our points into, or our points into the partial derivatives. Okay, so fx at 3, 4 would be 3 over 5. And fy would be 4 over 5, okay? Okay then. And, I think I'll go ahead, not necessary, but I'm going to write it as a decimal. So that's 0.6 and that's 0.8. Okay, good. So then let's compute the differential first, okay? So remember the formula for the differential was roughly fx, well I'll write it out. So it's fx at the point times x minus x naught, and then plus fy at the point, and times y minus y naught, okay? So let's plug in all of our numbers. So fx ended up being 0.6. Okay. We know x naught is 3. And we know y naught is 4. Okay. What are we plugging in for x and y?
The 2.9 over.
Yeah, that's right, yeah. because we're trying to approximate our function at this xy value. So plug in 2.9, we'll plug in 4.2 here. And if I compute all of that, let's see here, I think that would be negative 0.06. So B 0.16, I believe. So I think it's 0.1 altogether, all right? So then finally, to get our approximation at this point. So we know it's approximately our linearization.
Just add the 5.
Yeah. So I'll write this out. And then f of x naught y naught was 5. And dz was 0.1. So it's approximately 5.1. Okay?
So it's basically the same thing, but it's just separating the other part into DC and
If
calling
you
it a
will.
differential.
Yeah. Now I will say one thing is that if the question asks you to approximate this, okay? So if they ask you to approximate like not just f of xy, but a change in f, then that would just be the differential, okay? So they're kind of like the same thing. The only thing is if you're just calculating the differential, then it would just be like you're moving this to the other side, and you're calculating the change in z instead of the function at a certain point, okay? All right. Let's see here. So these are just sort of like kind of silly examples, perhaps, of how we can use the linearization to approximate our function. So it's kind of silly because you can just plug the numbers into a computer or a calculator and get more exact values. Okay. But this idea of approximation it's like very important, if you say. So a typical situation in which we use linearizations which you guys might encounter perhaps if you take more classes. Sometimes you have an equation in which you're trying to solve like of this form, a function equal to some constant. So if you approximate your function with the linearization, then what you can do is solve this equation instead. This equation will be easier because your linearization is always like a really simple looking function. So the linearization, if I just go back to like one example real quick. Okay, so it always looks something like this, constant times x minus x naught plus constant times. So it's always a really simple function. So the idea is like this equation is typically easier to solve. And if your linearization is approximately the same as your function, then the idea is a solution to this equation should be approximately also a solution to the original equation. Okay? So I'll say a solution to the linearized problem should be approximately a solution to the original problem. So this simple idea forms the basis of various numerical algorithms for finding solutions to equations. One that you might have heard of is Newton's method. I'm not going to go into it, but I'm just kind of letting you know that this idea has applications to other things, okay? All right. Any questions about that? Yes.
What is the change in
Yeah.
change in
Change in z. So your differential will approximate the change in z or the change in your function at 2 points. Okay, I thought I might sneeze again. So the actual change in z, like the actual change in your function between 2 points, I guess like notation-wise, people often use delta z for the actual change in z, whereas dz is an approximation of it. Okay. I don't know if that answered your question. Okay, good. All right. I think I'll just touch on one more thing real quickly. So just real quickly, wanted to talk about partial differential equations. So what is a partial differential equation? It's an equation involving partial derivatives of some function. Okay. And so just like some examples of partial differential equations which have applications in physics. So one equation is Laplace's equation. So Laplace's equation is uxx plus uyy equals 0. And it's maybe not too important for you guys, but this expression, uxx plus uyy, that is called the Laplacian of u. And people often denote it as like this. Okay. That's maybe not super important, but I just thought I would let you know. Other equations which are important in physics, I'll maybe just do one more, so the wave equation. So the wave equation looks like this. UTT equals c squared times uxx. Okay. So the wave equation describes like motion of a wave, and Laplace's equation is related to steady state temperature distributions in like objects, if you will. Okay. And so just like a quick example involving a partial differential equation. So here I'm just going to write out a function, u of xt equals sine of kx minus omega t. So k and omega are just constants, and x and t are the actual variables, okay? And so you guys, if you took physics 1, then all of you guys learned that this describes the motion of a point on a wave, or sorry, on a string. If you're like moving the string up and down, So I'll draw a picture. Like you have a string. Imagine taking the end and just moving it up and down. As you move the string up and down, what happens is a wave starts forming and starts traveling along the string, right? I don't know if you guys understand what I'm trying to draw here. Okay, all right. So like if you keep moving it up and down, you're gonna get a nice wave moving along that string, okay? So let's imagine like this is our x-axis. So at a certain point x, you can ask like, how does the position of this point on the string oscillate up and down at this point? And the motion is described by this equation up here, okay? And so it should be no surprise that this function satisfies the wave equation. Specifically, it satisfies this equation, u to t equals c is omega over k uxx, okay? So maybe I'll phrase it like this. It satisfies the wave equation utt is c squared uxx, where the constant c is specifically equal to omega over k. All right? And if we just do like a quick computation just to verify that this function is a solution to the wave equation. So given this function u up here, let's compute the partial derivatives. So I want to compute uxx and utt, okay? So let's get ux first. So who can tell me what ux will be? So partial derivative, yeah, with respect to x.
Cosine
Uh-huh.
of kx minus wt.
And that times
and
k, right?
then-
Yep.
Yeah, k.
And we want uxx, so tell me what that will be.
Negative k sine of the, it'll be k squared, right?
Yeah, okay,
And then sine.
good. Let's also get ut.
Cosine of kx minus the wt, or like omega t.
Mm-hmm.
And then w on the outside.
All right. And just omega or
Omega.
Negative
negative as well, yeah. Okay, all right. And then let's compute utt.
negative omega squared. And then sine,
Sine.
sorry. Omega squared,
No,
right?
it's negative because it'll be negative.
Yeah, so a lot of negatives there. So cosine gives you a negative
Oh, yeah,
sign,
negative sign.
but then
Yeah.
another
Yeah.
negative. Okay, good. It's very tricky, but okay. So then, this is utt. So if we look at c squared uxx, where c is omega over k. So I'm going to have c squared times uxx, okay? So what happens, the k squareds will cancel out, and you should be left with negative omega squared sine of kx minus omega t, okay? So yeah, so our function satisfies the wave equation, and that utt is equal to c squared uxx, all right? Okay, That's really all I wanted to do with partial differential equations. Do you guys have any equations or any questions for me?
No.
The review goes to 4:15. I have a couple more minutes, so maybe let's talk a little bit more about other stuff, okay? All right. Have you guys talked about the gradient yet?
No.
No, okay. Okay. You guys have talked about, I guess, the chain rule, though. Yeah. Okay. Maybe I'll kind of, I'll save it for next time if it's only 7-ish minutes left, okay? So I'll end my review here.